The universe is dying right now. Not slowly fading, not gently winding down, dying. And it has been dying since the moment it was born. Right now, stars are running out of fuel, galaxies are drifting apart. The raw material needed to form new stars is being used up and never replaced. The universe is burning through its reserves, and there is no resupply coming. And we know exactly how it ends. Not in rough terms, not in vague gestures toward heat death, in precise scientific detail. We know the timeline, we know the stages. We know what the universe looks like at 10 to the power of 14 years, at 10 to the power of 40, at 10 to the power of 100. And every single stage is darker and colder and emptier than the one before it. Here is the complete timeline of everything that has ever existed and exactly when it all ends. Welcome to Void Atlas. I'm your host, and today we're going to the end of everything. Not metaphorically, not philosophically, physically. Step by step, era by era, with the actual numbers that physicists have calculated for how the universe dies. Before we begin, I want to make sure you understand the scale of what we're talking about. Because the human mind is not built for the time scales we're about to discuss. The age of the universe right now is roughly 13.8 billion years. That's a number most people can at least gesture toward. The universe is old. We get it. But the timescales of cosmic death make 13.8 billion years look like a rounding error. We're going to be talking about numbers like 10 to the power of 40, 10 to the power of 100, 10 to the power of 10 to the power of 76. Numbers that are not just large, but almost categorically beyond comparison to anything in human experience. So let me give you a frame before we start. Think of the current age of the universe as 1 second. 1 second. By that comparison, the last star in the universe won't die for about 10 million years. Not 10 million years, 10 million seconds. We're using a metaphor where the age of the universe is 1 second, and the last star burns for 10 million of those seconds. And that's just the beginning. The timescale of total cosmic death, by this comparison, would be a number so large I couldn't read it aloud in a human lifetime. The universe is going to last for an almost incomprehensible amount of time. But it will not last forever. And every moment from now until the absolute end is a step in one direction, toward a darkness so complete and so permanent that not even time will have any meaning inside it. Let's start at the beginning of the timeline, where we are now. We are currently living in what cosmologists call the stelliferous era. Stelliferous, from the Latin stella, meaning star. The era of stars. It began about 100,000 years after the Big Bang, when the universe had cooled enough for the first stars to ignite. And it will end, by the best current estimates, in about 100 trillion years, or 10 to the power of 14 years. 100 trillion years. That's about 7,000 times longer than the current age of the universe. And we are here, inside it, so early in the stellar era that we're essentially at the very beginning. We haven't even hit 1% of the stelliferous era's total duration. In this era, the universe is alive in a way that it will never be again. Stars form from collapsing clouds of gas and dust, fuse hydrogen and helium in their cores, shine for millions or billions or trillions of years, and then die. Their deaths scatter heavy elements, carbon, oxygen, iron, gold, into space, enriching the gas clouds that will form the next generation of stars. The universe is a cycle of stellar birth and death, and that cycle produces everything we call complexity, chemistry, planets, life. But here's the thing. The cycle is not sustainable. The universe has a finite supply of hydrogen, and hydrogen is the fuel that powers stars. Every star that forms uses up some of that hydrogen, converts it to heavier elements, and those heavier elements never become hydrogen again. The supply is being drawn down, and there is no mechanism to replenish it. Right now, the rate of star formation in the universe is already much lower than it was in the past. The peak of star formation, the moment when the universe was making new stars faster than at any other time, happened about 10 billion years ago, approximately 3.8 billion years after the Big Bang. Since then, the rate has been declining. We are past the universe's peak productivity. The universe is already, in a very real sense, past its prime. But there are still new stars forming. There will continue to be new stars forming for a very long time. The small, dim red stars, called red dwarfs or M-type stars, are extraordinarily efficient with their fuel. A red dwarf with a fraction of the sun's mass can burn for trillions of years. Some red dwarfs are expected to shine for as long as 10 trillion years. 10 to the power of 13 years. That's almost 1,000 times longer than the current age of the universe for a single star. These red dwarfs will be the last fires in the universe, long after stars like our sun have faded and died, long after the Milky Way as we know it has changed beyond recognition. Red dwarfs will still be burning. Small, dim, reddish-orange, but burning. Until about 10 to the power of 14 years from now, when the last red dwarf exhausts its hydrogen and goes dark, and the stelliferous era ends. Let me put that moment in context. After 10 to the power of 14 years, there are no more stars. Not dying stars, not dying soon stars, no stars at all. The universe goes from a place of fire and light, billions of galaxies, each containing hundreds of billions of stars, to a place of darkness, inhabited only by the remnants of what stars used to be. What are those remnants? 3 kinds of dead stars. White dwarfs, the hot, dense cores of stars like our sun, slowly cooling over unimaginable timescales. Neutron stars, the ultra-dense remnants of massive stellar explosions, mostly dark, mostly cold. And black holes, the ultimate stellar remnants, objects so dense that light itself cannot escape. the only things in the universe that can in some sense be said to last forever. At 10 to the power of 14 years, the stelliferous era ends and the degenerate era begins. This is the era of dead stars, an era of white dwarfs slowly cooling, of neutron stars spinning down, of black holes dominating the gravitational landscape. How long does the degenerate era last? About 10 to the power of 40 years. That number, 10 to the 40, is 10 billion times 10 billion times 10 billion times 10 billion years. Your mind cannot picture it. Nobody's mind can. It is genuinely incomprehensible. And yet, it is a specific, calculated number that physicists have derived from the physics of white dwarf cooling and stellar decay. But wait, I said white dwarfs cool slowly over unimaginable timescales. How slowly? A white dwarf starts out incredibly hot, tens of thousands of degrees at its surface. But it has no energy source. It's just a hot ball of carbon and oxygen, radiating its heat away into the surrounding universe. Over time, over astronomical timescales, it cools. It fades from white to yellow to orange to red to dim infrared to nothing. Eventually, after roughly 10 to the power of 37 years, a white dwarf that has been cooling since the end of the stelliferous era becomes what is called a black dwarf, an object with the mass of a dead star, the size of a planet, and the temperature of the surrounding universe, essentially zero. Black dwarfs are theoretically the ultimate fate of stars like our Sun. But here's something remarkable. There are no black dwarfs in the universe right now. Not a single one. Because the universe hasn't been around long enough for any white dwarf to cool all the way down to black dwarf status. Every white dwarf that has ever formed is still radiating heat. Some of them are still hot. The universe is not old enough for the cooling process to be complete even once. In 10 to the power of 37 years, the cooling process completes. White dwarfs become black dwarfs. The degenerate era winds down. And something even stranger is expected to happen. Proton decay. Proton decay is a prediction of certain grand unified theories, theoretical frameworks that attempt to unify the strong nuclear force, the weak nuclear force, and the electromagnetic force into a single underlying theory. The standard model of particle physics, our current best description of the fundamental particles and forces, does not include proton decay. Protons, in the standard model, are stable. They last forever. But many extensions of the standard model, grand unified theories that try to go deeper to find the underlying unity beneath the forces, predict that protons eventually decay. Not immediately, not soon, but eventually. The predicted time scale for proton decay in many of these theories is around 10 to the power of 34 to 10 to the power of 40 years. If proton decay happens, it means that all the matter in the universe, all those black dwarfs, all those neutron stars, all the gas and dust and planets and asteroids and comets will eventually dissolve. One proton at a time, matter falls apart. Black dwarfs evaporate into elementary particles. Neutron stars dissolve. Everything made of ordinary matter slowly, over incomprehensible timescales, ceases to exist. We have not observed proton decay. Despite extensive experiments that have monitored enormous tanks of water or other materials, watching for any sign of a proton breaking down, we have never seen it happen. The experiments constrain the proton's lifetime to be at least 10 to the power of 34 years, consistent with theoretical predictions. But we haven't seen it. If proton decay does not happen, if protons are genuinely stable, then the degenerate era lasts much longer. The black dwarfs persist. The dead stellar remnants persist. The universe is dark and cold, but still contains matter. Either way, by 10 to the power of 40 years, the degenerate era ends. What remains? Black holes. And we have entered the black hole era. The black hole era is the universe's longest era by far. It lasts from roughly 10 to the power of 40 years to somewhere around 10 to the power of 100 years. That's the number 1, followed by 100 zeros. A Google years. And during almost all of that incomprehensible span of time, the universe is dominated by black holes. Objects that grow slowly by capturing any remaining radiation and particles, that eventually merge with each other where gravitational interactions bring them close enough, and that slowly, incredibly slowly, lose mass through Hawking radiation. We need to talk about Hawking radiation because it's the key to the universe's final act. In 1974, Stephen Hawking predicted, using a combination of quantum mechanics and general relativity, that black holes are not perfectly black. They emit a tiny, faint thermal radiation due to quantum effects near the event horizon. The rate of emission is inversely proportional to the black hole's mass. A small black hole emits more Hawking radiation than a large one, and therefore evaporates faster. A black hole with the mass of the Sun has a Hawking temperature of about 60 billionths of a degree above absolute zero, almost impossibly cold, and an energy output so faint it can't be measured with any current technology. But it's not zero. Over time, over vast, vast timescales, Hawking radiation causes black holes to lose mass and eventually evaporate completely. A solar mass black hole evaporating purely through Hawking radiation would take approximately 2 × 10 to the power of 67 years to evaporate. A supermassive black hole with the mass of 1 billion suns would take about 2 × 10 to the power of 83 years. And the largest black holes in the universe, with masses of many billions of solar masses, would take up to 10 to the power of 100 years. 10 to the power of 100 years. A Google. And after that, after the last, largest, most massive black hole in the universe finally evaporates in a final burst of Hawking radiation, the black hole era ends, and we enter the dark era. The dark era is the true end. After the last black hole evaporates, what remains? A thin, cold, dark, diffuse gas of elementary particles, mostly photons, the light emitted by all those stars over the stellar era, gradually redshifted by the expansion of the universe to wavelengths longer than we can imagine. Electrons and positrons, extremely sparsely distributed. Neutrinos. A universe so cold, so dark, so dilute, that no physical process of any significance can ever happen again. This is the heat death. Not death by fire, but death by cold. Death by the exhaustion of every available source of energy. Death by the universe reaching its maximum entropy. The state in which everything is perfectly, uniformly distributed, with no gradients, no differences, no structure that could possibly do any work or create any complexity. A universe in perfect, permanent, absolute equilibrium. The temperature in the dark era approaches, asymptotically, absolute zero. Not quite reaching it, quantum mechanics prevents that, but approaching it so closely that the difference is meaningless. The universe is essentially at zero temperature, zero energy gradients, zero entropy gradients, nothing left to do, nothing left to happen. And here is the most profound thing about the dark era. It doesn't end. There is no moment when the dark era concludes. There is no final event, no final transition, no moment when the universe stops and something else begins. The dark era simply continues forever. Temperature staying essentially at zero, the thin gas of photons and particles becoming ever more diffuse as the universe continues to expand. And nothing happening. If you are a being of thought and awareness, the dark era is the most horrifying place in the universe's history, because it is not merely the end of life, it is the end of change, the end of events, the end of the very possibility of anything happening. In the dark era, time has no meaning. Not because time doesn't pass, but because nothing marks its passage. Nothing changes. Nothing happens. Time becomes, in a very real sense, indistinguishable from no time at all. Now, let me stop here and make sure you understand what we've just been through. Because we just covered a timeline so vast that the current age of the universe doesn't even register as significant on it. We are at 13.8 billion years, 10 to the power of 10 years. The stellar era ends at 10 to the power of 14 years. The degenerate era ends around 10 to the power of 40 years. The black hole era ends around 10 to the power of 100 years. And then the dark era begins and never ends. The ratio of the black hole era's duration to the current age of the universe is the same as the ratio of the universe's age to the smallest possible time interval in physics, the Planck time. The mathematics of the end of everything is fundamentally, categorically beyond human intuition, and yet it is as well supported as any other prediction in cosmology. This is not speculation. This is physics. Now, I want to take a step back from the timeline itself and ask a question that I think deserves serious attention. What does it mean for the universe to die? And I want to offer something that might surprise you. In a very real sense, the universe doesn't die. It transforms. It becomes something that is not compatible with any of the processes we associate with life or activity or meaning. But it doesn't cease to exist. The matter and energy in the universe are conserved. They don't disappear. They persist in the most diffuse and structureless form possible for what might be an infinite amount of time. What ends is not the universe's existence. What ends is its ability to produce complexity, its ability to generate structure, its ability to create and sustain the conditions under which interesting things happen. Stars, planets, chemistry, biology, thought, all of these require energy gradients. They require differences in temperature, in density, in chemical composition. They require the universe to be out of equilibrium, to have some regions hotter than others, some regions denser than others. Life and complexity are not things that happen when everything is uniform. They are things that happen at the boundaries between differences. And the universe's death, its heat death, is the final erasure of all boundaries, the final smoothing out of all differences. The universe ends not with a bang, but with the most profound possible silence, the silence of perfect, permanent uniformity. Now, before I forget, and I'm reminding you intentionally, because what we're talking about is genuinely overwhelming, and I want you to be there for all of it. If this kind of deep dive into the universe's biggest questions is what you come to Void Atlas for, subscribe. Hit that button. Every week we go somewhere new, somewhere difficult, somewhere that doesn't have easy answers. This is a community of people who take the universe seriously, and I would love for you to be part of it. Let me now go back into the timeline and fill in some details I passed over, because the full story of how the universe dies is richer than I've described so far. Let me tell you about some of the specific events within these vast eras, events that are predicted by physics and that paint a more detailed picture of the universe's slow unraveling. We're still in the stelliferous era right now, but within the next few billion years, our own cosmic neighborhood is going to change dramatically. In about 5 billion years, our sun will exhaust the hydrogen in its core and begin to expand into a red giant. It will grow so large that it may swallow Earth entirely, or at least heat it to temperatures that make any form of life impossible. Mercury and Venus will certainly be consumed. The sun will then shed its outer layers as a planetary nebula, leaving behind a white dwarf, a dense, hot core about the size of Earth, slowly cooling over the next billions of years. Before that happens, in about 4 billion years, the Milky Way and the Andromeda Galaxy will collide. This is not a collision in the dramatic, explosive sense. Galaxies are so diffuse that individual stars rarely actually collide when galaxies merge. But the gravitational interaction will reshape both galaxies dramatically. Stars from both will be flung into new orbits. The shapes of both galaxies will be destroyed. The merger will take about 2 billion years to complete, and the result will be a new, larger elliptical galaxy that some astronomers have proposed naming Milkomeda. In roughly 100 billion years, 10 to the power of 11 years, dark energy will have pushed all galaxies outside our local group so far away that they will no longer be visible from inside the Milky Way. The universe beyond our immediate cosmic neighborhood will have disappeared behind the cosmological horizon, receding faster than light. Any civilization inside Milkomeda at that point, looking out at the sky, will see nothing but their own galaxy. The rest of the universe will be invisible, not just dark, gone in every practical sense. In 10 to the power of 12 years, a trillion years, the last red dwarfs are still burning. The universe is populated by dim, small, reddish stars scattered across a vast and mostly dark universe. New stars are no longer forming. The raw material is exhausted. What remains are only the stars that formed long ago, burning slowly on their last reserves of hydrogen. In 10 to the power of 14 years, the last red dwarf goes dark. The stelliferous era ends. The universe is now populated only by white dwarfs, neutron stars, black holes, and the cold debris of stellar deaths. Planets, asteroids, rocky remnants, frozen gas. It is dark. It is cold, and it will be this way for an almost incomprehensible length of time. In 10 to the power of 15 years, all planetary orbits become randomized. Gravitational interactions between stellar remnants over enough time give every body in a system enough random kicks to eventually either fling it out of the system entirely or cause it to spiral inward. Planets and asteroids are scattered. The orderly solar systems that formed billions of years earlier are disrupted. What remains are isolated objects drifting through the dark. In 10 to the power of 19 years, stellar remnants within galaxies interact through gravitational scattering over sufficient timescales that the galaxy itself begins to evaporate. Stars gain enough energy from gravitational interactions to escape the galaxy entirely. At the same time, the remaining mass sinks toward the galactic center, feeding the central supermassive black hole. Galaxies, in the very long run, are not stable. They too evaporate. In 10 to the power of 20 to 10 to the power of 30 years, if proton decay happens, ordinary matter begins to disintegrate. One proton at a time, the baryonic material of the universe dissolves. Black dwarfs, neutron stars, rocky planets, asteroids, all matter falls apart into elementary particles. The universe becomes even more diffuse, a gas of leptons and photons. In 10 to the power of 67 years, solar mass black holes evaporate through Hawking radiation. A black hole with the mass of our Sun, which formed at the end of a stellar life billions of years into the stelliferous era, finally radiates away its last particle and disappears in a final burst of high-energy photons. In 10 to the power of 80 to 10 to the power of 100 years, the supermassive black holes that formed at the centers of galaxies evaporate. These are the largest, most massive, most long-lived objects in the universe. A black hole with 10 billion solar masses, comparable to the largest black holes we've observed, takes roughly 10 to the power of 98 years to evaporate, and in its final moments, as it loses the last of its mass, it radiates with increasing intensity, producing a brief final flare of light in a universe that has been dark for almost as long as it is possible to conceive. And then it is gone. and the universe is left with nothing but the diffuse cold gas of photons and particles. The dark era, forever. There are some additional timescales worth mentioning, even more exotic and speculative, that some physicists have calculated for events that might occur during the dark era. Events that arise from the statistical nature of quantum mechanics and that would require almost literally infinite time to occur. In 10 to the power of 10 to the power of 50 years, quantum tunneling allows frozen objects, the remnants of matter that survived proton decay somehow, or objects in configurations we haven't fully considered, to undergo a process called quantum tunneling, in which matter spontaneously rearranges itself into lower energy configurations. Atoms and molecules, in the extraordinarily rare event of collective quantum tunneling, could rearrange themselves into iron, which is the most stable configuration of nuclear matter. Over timescales of 10 to the power of 10 to the power of 15 years, all matter, if any ordinary matter still exists, would have tunneled into iron configurations, and in timescales so vast they defy any attempt at metaphor, numbers like 10 to the power of 10 to the power of 76 years, the most extraordinary thing predicted by quantum mechanics might happen. A Boltzmann brain. A Boltzmann brain is a thought experiment proposed by the Austrian physicist Ludwig Boltzmann in the 19th century. The idea comes from statistical mechanics, the physics of large numbers of particles and their collective behavior. In statistical mechanics, any physical configuration, no matter how unlikely, has a non-zero probability of occurring spontaneously as a random fluctuation. If you wait long enough, and in the dark era, you have effectively infinite time. Any configuration of matter can occur. A Boltzmann brain is a self-aware mind that spontaneously arises as a random quantum fluctuation from the background of the universe. Not as the product of evolution and biology, but purely by chance. A brain-sized cluster of particles that happens, through the random fluctuation of quantum fields, to arrange itself into a configuration that constitutes a conscious mind, complete with memories, sensations, and thoughts, and that then, in the next instant, dissipates back into the void. This is not science fiction. It is a genuine prediction of the mathematics of statistical mechanics applied to an infinite, or effectively infinite, timescale. The timescale for a Boltzmann brain to spontaneously fluctuate into existence is something like 10 to the power of 10 to the power of 50 years, a number so vast that even the Google years of the black hole era is, by comparison, a rounding error. But in an infinite dark era, even this probability eventually becomes effectively inevitable. And if Boltzmann brains are real, if the mathematics is right, then the universe's history is dominated in terms of total conscious experience, not by the brief, bright, stelliferous era with its biology and civilizations, but by the countless, lonely Boltzmann brains flickering briefly into consciousness in the cold, dark, empty universe of the far future, experiencing something, a memory, a sensation, a thought, and then vanishing. This is the part of cosmology that I find most genuinely disorienting. The idea that if the universe is infinite in time, then most conscious experiences in it might be experienced by random fluctuations in a dark void, rather than by evolved beings in a warm, living world. The idea that the universe's brief, brilliant, meaningful period, the era we live in, might be, from the perspective of total conscious experience across all of time, completely negligible. We don't know if Boltzmann brains are real. There are serious arguments against taking this prediction at face value. The probability is almost incomprehensibly low. The thermodynamic arrow of time might prevent such fluctuations in ways we don't fully understand. Many physicists treat the Boltzmann brain problem as a reductio ad absurdum, a sign that certain cosmological models need revision rather than a genuine prediction about the universe's future. But it is a genuine consequence of the mathematics, and it serves as a reminder of how strange things become when you take the full implications of physics seriously and extend them across the timescales the universe has available. Let me now talk about something that many people, when they first encounter the full timeline of cosmic death, want to know. Is there any escape? Is there any way around this? Could a sufficiently advanced civilization somehow avoid the heat death of the universe? The honest answer is, not with any physics we currently know. The second law of thermodynamics, the law that says entropy always increases in a closed system, is one of the most robustly tested principles in all of physics. It is not just an empirical observation. It follows from the fundamental laws of statistical mechanics. In a universe with a finite amount of matter and energy, evolving according to known physical laws, heat death is inevitable. But here's where I want to be honest about uncertainty. Our knowledge of physics is not complete. We don't understand dark energy. We don't have a theory of quantum gravity. We don't fully understand the nature of time or entropy at the deepest level. And there is a long history in science of physical limitations turning out to be limitations of our current understanding rather than fundamental limitations of nature. Freeman Dyson, the brilliant theoretical physicist who worked at the Institute for Advanced Study in Princeton, wrote a famous paper in 1979 called Time Without End: Physics and Biology in an Open Universe. In it, he argued that in a universe that expands forever but does not end in heat death, a universe where the energy budget is more generous than the standard model predicts, life could potentially survive and think indefinitely, using ever-diminishing amounts of energy and slowing its metabolism proportionally. Life could persist by going into increasingly long periods of hibernation, waking up to think briefly, then hibernating again, extending its total experience over infinite time using finite energy. Dyson's argument was elegant and optimistic. And it doesn't apply in a universe dominated by dark energy, because dark energy changes the structure of the universe in ways that close off Dyson's escape routes. The accelerating expansion powered by dark energy means that the universe's energy budget is not as flexible as Dyson assumed. But the spirit of Dyson's inquiry remains. The spirit that says, before we accept a conclusion as inevitable, we should make sure we've truly understood all of physics. And we haven't. We are at a very early stage in understanding the universe. Dark energy is 25 years old as a discovery, and we have essentially no idea what it is. The complete physical picture of the universe's future is not yet available to us. So here is where I want to land, after taking you through the complete timeline of cosmic death. After 10 to the power of 14 years, the end of stars. After 10 to the power of 40, the end of ordinary matter. After 10 to the power of 100, the end of black holes. After the dark era, the end of change. After Boltzmann brains in the inconceivable far future. I want to land on something that I think is genuinely true and genuinely important. The universe we live in right now, today, is the most alive the universe will ever be again. Not the most alive it has ever been. We are past the peak of star formation, as I mentioned, but more alive than it will ever be from this point forward. The rate of star formation, the amount of light in the universe, the complexity of structures and processes, all of it peaks in the deep past and has been declining ever since. And it will continue to decline forever. We are living in the universe's afternoon. The morning was billions of years ago. The night is coming. Not soon. Not for a timescale that has any meaning for human civilization or human concern, but coming. And that means this era, this moment. This brief period when stars burn and planets warm, and chemistry happens, and minds think, and civilizations build, and questions get asked. This is it. This is the apex. This is the zenith of what the universe can do. Everything before this led to it. Everything after this leads away from it. We are the universe at the height of its ability to be interesting. That is not a small thing. That is not a reason for despair. It is, if anything, a reason for a very particular kind of awe. The universe has gone to enormous trouble, 13.8 billion years of trouble, to produce a moment in which something complicated enough to ask questions about its own fate came into existence. And that moment on the cosmic timeline is so brief that it barely registers. And it is now. We are here, right now, in the most improbable, most extraordinary, most fleeting moment in the entire history of a universe that will last for a Google years. How do you feel about that? This has been Void Atlas. I'm your host, and this video, this particular journey, is one I find genuinely moving every time I think about it. Not because the end of the universe is sad. On the timescales we've been discussing, nothing that happens to us matters in a thermodynamic sense. But because the sheer improbability of the moment we're living in, placed against the vast darkness that precedes and follows it, makes the light seem all the more extraordinary. 10 to the power of 14 years until the last star burns out. 10 to the power of 100 years until the last black hole evaporates. And then forever. And we are here, in the middle of it, asking what it means. Subscribe to Void Atlas. Come back next week. There is still so much universe to explore. And while the stars last, we might as well explore it. I'm your host, thank you for being here. Until next time, look up while there's still something to look at. But I am not done, because there are things about the universe's death that I haven't told you yet. Pieces of the timeline that add texture and depth to the story. Events within these vast eras that paint a more complete picture of how the universe unravels. Let me tell you about what happens to galaxies themselves. We tend to think of galaxies as permanent features of the universe. The Milky Way has been here for about 13 billion years. It will be here for another several billion years in its current form. But over the time scales we're discussing, 10 to the 40, 10 to the 50, even galaxies are temporary. Within the first trillion years of the stelliferous era, the shape of galaxies changes dramatically as star formation slows and then stops. Galaxies become populated increasingly by dim, old red stars and white dwarfs. Their spiral arms, maintained by ongoing star formation and the density waves that trigger it, fade and dissolve. Galaxies become more amorphous, more irregular, as the dynamic processes that maintain their structure cease. By 10 to the power of 15 years, most galaxies have lost their recognizable form. What remains are loose associations of stellar remnants, bound together gravitationally, but no longer resembling the magnificent spiral structures we see today in photographs from the Hubble Space Telescope. By 10 to the power of 19 to 10 to the power of 20 years, gravitational interactions between stellar remnants within what used to be galaxies cause those structures to evaporate. Individual stars gain enough energy from gravitational encounters to escape the galactic gravitational well entirely. Most of the mass of a former galaxy gets ejected this way, flying off into the intergalactic void as isolated objects. White dwarfs, black dwarfs, neutron stars, drifting in complete darkness through an empty universe. A small fraction of the mass sinks toward the center, falling into the central black hole and feeding it. But even this feeding process slows as the available material thins out. By 10 to the power of 20 years, galaxies as gravitationally bound structures have largely dissolved. The universe is no longer a collection of galaxies. It is a dark, nearly empty space with isolated objects drifting through it and black holes scattered through the void. Now let me tell you about something that happens on the scale of black holes. Something specific and dramatic that most timelines skip over. The black hole merger events that occur during the black hole era. As galaxies evaporate over 10 to the power of 19 to 20 years, many of the stellar remnants that escape into the void carry kinetic energy and angular momentum. But some don't escape. They fall toward the galactic center. Over even longer timescales, the distribution of mass in the universe changes. Black holes that formed at the centers of galaxies grow as material falls in during the galactic evaporation process. Then, when two former galaxies interact gravitationally, even over the vast distances of the dark universe, their central black holes may eventually spiral toward each other and merge. Black hole mergers produce gravitational waves. In the stelliferous era, black hole mergers have been detected by LIGO, the Laser Interferometer Gravitational Wave Observatory, as brief chirps of space-time rippling. But in the black hole era, as the last supermassive black holes merge over billions upon billions upon billions of years. The gravitational waves they produce are not brief chirps, but long, slow, incredibly low-frequency undulations in space-time. Wavelengths measured not in meters, but in light-years. Frequencies so low that a single cycle would take thousands of years to complete. These are the last events of consequence in the universe, the last moments of activity. Two supermassive black holes, each containing billions of solar masses, spiraling together over millions of years, emitting slow gravitational waves that ripple through an otherwise silent universe, and finally merging in a burst of energy that briefly, for a cosmic instant, makes the resulting black hole the most energetic thing in the universe. And then silence again. And then the merged black hole begins to evaporate, slowly, imperceptibly, over googles of years. Let me also talk about something that doesn't get enough attention in discussions of the universe's end: the role of dark energy in shaping the final timeline. Dark energy is not just accelerating the expansion of the universe today. It is changing the geometry of the universe's future in ways that affect every aspect of the timeline I've described. The specific nature of dark energy, which we don't understand, determines which version of the universe's death actually occurs. In the model I've been describing, dark energy has a constant energy density. This is called the cosmological constant, and it was Einstein's original formulation. In this model, the expansion of the universe accelerates, but in a controlled way. The universe expands forever, getting ever larger and ever more dilute, but the expansion rate stabilizes. The death of the universe in this model is the heat death I've described: slow, cold, and complete. But dark energy might not be constant. If dark energy's density increases over time, a possibility that some current observations slightly favor, according to certain interpretations of recent data from the Dark Energy Spectroscopic Instrument, then the universe faces a different fate, one that is much more dramatic and much more sudden. This alternative is called the Big Rip. In the Big Rip scenario, dark energy's density grows over time. The expansion of the universe accelerates more and more. At first, this just means galaxies recede from each other faster than in the cosmological constant model. But eventually, the expansion rate grows so large that it overwhelms gravity on smaller and smaller scales. Galaxies get ripped apart. Then stellar systems get ripped apart. Then individual planets get ripped apart. Then atoms get ripped apart. And finally, even subatomic particles are torn apart by the expansion of space. The Big Rip would happen at a specific, calculable time, in some models about 22 billion years from now. Not the far future timescales of heat death, but the relatively near future from a cosmological perspective. The current age of the universe is 13.8 billion years. If the Big Rip happens in 22 billion years, the entire future of the universe, from now until the end of everything, is only about 60% longer than its current age. In Big Rip models, there is no era of dead stars, no era of black holes, no dark era. The universe ends abruptly, violently, on a human comprehensible timescale. Current observations suggest that dark energy is consistent with a constant, the simplest cosmological constant model. But the uncertainty is large enough that the Big Rip cannot be ruled out. We don't know. There is also a scenario that goes in the opposite direction. If dark energy is not constant but decreasing, if the cosmological constant is decreasing over time, then the expansion of the universe might eventually reverse. The universe might stop expanding and start contracting. If this happens, the big crunch awaits. All matter in the universe falls toward each other as space contracts. Galaxies collide and merge. Stars collide. The temperature of the universe rises, and eventually, in a scenario that is the reverse of the Big Bang, the universe collapses back into a singularity of infinite density. Everything that exists compressed into an infinitely small point, and then gone. The Big Crunch, if it happens, would likely occur on timescales of tens to hundreds of billions of years, comparable to or shorter than the Big Rip timescale. Current observations strongly favor a universe that will expand forever, which rules out the Big Crunch in standard models. But again, we don't fully understand dark energy. And then there is the false vacuum scenario. This is perhaps the most existentially unsettling possibility of all, and it comes not from cosmology, but from particle physics. In quantum field theory, the vacuum is not empty. Empty space is filled with quantum fields, and those fields have a lowest energy state, a vacuum state. The Higgs field, which gives mass to particles, and which the Large Hadron Collider confirmed by detecting the Higgs boson in 2012, has a vacuum state that might not be the true lowest energy state. In other words, the vacuum of our universe might be a false vacuum, not the true minimum of the Higgs field's potential energy, but a local minimum, a temporary resting place that is stable enough to persist for a very long time, but not stable enough to last forever. The true minimum, the true vacuum, might have a different, lower energy. If the Higgs field tunnels from our false vacuum to the true vacuum, a process that could happen spontaneously anywhere in the universe at any time, it would create a bubble of true vacuum expanding outward at the speed of light. Inside that bubble, the laws of physics are different from the laws of physics in the false vacuum we inhabit. Not subtly different, completely different. Different masses for particles, different strengths of forces, almost certainly incompatible with any form of structure, chemistry, or life. This bubble of true vacuum would expand outward from its origin at the speed of light, converting everything it encounters from the false vacuum to the true vacuum. And because it expands at the speed of light, there is absolutely no warning. No signal can outrun it. You cannot see it coming. One moment you exist, the next moment you don't. Not because you were hit by anything, but because the very framework of physics that makes you possible was replaced by a different framework. And what makes this particularly unsettling is that we might already be in a false vacuum. The measurements of the Higgs boson's mass from the LHC, combined with the top quark's mass, suggest that the Higgs field is in a state that could be a metastable false vacuum. If it is, the timescale for spontaneous vacuum decay, the formation of a true vacuum bubble, is estimated to be vastly longer than the current age of the universe. Trillions upon trillions of years.
probably long enough that other aspects of the universe's death, proton decay, black hole evaporation, would occur first. But probably is not certainly. And we don't know for sure that we're in a false vacuum.
And we don't know the exact stability of the Higgs field with enough precision to be certain. The uncertainty is real. If vacuum decay happens, the timeline I described earlier is replaced by something much more abrupt. No long stellar era, no degenerate era, no black hole era, just an expanding bubble of new physics sweeping through the universe at the speed of light, and then a universe with completely different laws in which nothing we know is possible. This is one reason some physicists argue that false vacuum decay, if real, might be the most important unknown in all of physics. Because it means the entire future I've been describing, the 100 trillion years of stellar burning, the Google years of black hole evaporation, might be replaced by something that happens much sooner and much more suddenly. We don't know. We genuinely do not know. And I think that honest uncertainty is one of the most important things I can leave you with. Because the full timeline of the universe's death, as detailed and as precise as it is in many of its predictions, depends on things we don't yet understand. Dark energy, proton stability, the stability of the Higgs field, quantum gravity effects at extreme timescales. Each of these introduces genuine uncertainty into the picture. What we can say with confidence is this: the universe is not eternal. It has a beginning, it has a middle, and it has an end. Or rather, a slow, gradual transition into a state so cold and so empty and so unchanging that calling it an end is the only word available to us. And the era we live in, the era of light and fire and complexity, is extraordinarily brief by the standards of cosmic time. We are in a special moment, a moment that will not be repeated, a moment that took billions of years to arrive and will be over. On cosmic timescales, essentially as soon as it began. What do you do with that? How do you hold it? I think the only honest answer is with wonder. With the full weight of what it means to be a mind in a universe that is, for this brief and precious moment, alive in a way it will never be again. To be the universe's way of knowing itself during the one era when there is something worth knowing. To be here, asking questions, making sense, building knowledge. While the stars still burn and the light still travels and the universe still has something to say. We are in the right place. We are in the right moment. We are, against almost incomprehensible odds, here, in the afternoon of the universe, in the brief and extraordinary window when complexity is possible. Make something of it. This is Void Atlas. I'm your host. Thank you for spending the end of the universe with me. Every week, we take on a question this big and this serious. And every week, I am amazed that we get to do it together. Subscribe to Void Atlas. Come back next week. The universe is dying, but it's doing it beautifully, and we have time to watch. Until next time, keep looking up. The stars are still there. For now. Actually, I want to go one more place before we're truly done, because there's a dimension of this topic that I haven't addressed, and I think it's the most philosophically important one. What does it mean for the universe to be dying if we are inside it? How should we feel about the fact that everything we know and love and value is temporary? Not temporary in the human sense, lasting a few decades or centuries. Temporary in the cosmic sense, lasting a few 100 trillion years at most, before darkness falls and nothing is left. This question connects to some of the deepest problems in philosophy. The problem of meaning in a finite universe. The problem of whether human values and human accomplishments are real if they don't last forever. The problem of what, if anything, makes existence worthwhile when existence has an end. Different philosophical traditions have grappled with these questions in different ways, and I want to take them seriously, not as abstract puzzles, but as genuine questions about how to live in the kind of universe physics tells us we inhabit. The Stoic philosophers of ancient Greece and Rome, Epictetus, Marcus Aurelius, Seneca, dealt with finitude by making a distinction between what is in our control and what is not. The death of the universe is not in our control. The heat death is coming. The stars will go out. But how we live in the meantime, what we value, what we create, how we treat each other, these are within our control, regardless of how the story ultimately ends. The Epicurean tradition offered a different response. Death is nothing to fear, Epicurus argued, because when death comes, we will not be there to experience the loss. The same logic applies scaled up. When the last star goes out, there will be no one to mourn it. The darkness of the dark era is not experienced by anyone as darkness. It simply is. And a state of affairs that no one experiences is neither good nor bad. Buddhist philosophy offers yet another framing. Impermanence, anicca, is not a problem to be solved, but a fundamental feature of reality to be understood and accepted. Everything that arises passes away. This is true of thoughts, of relationships, of civilizations, of stars, of the universe itself. And the acceptance of impermanence in Buddhist thought is not despair, but liberation. When you stop grasping at permanence, you can be fully present in the moment that is. I don't want to claim that any of these philosophical traditions has the definitive answer, but I find something useful in each of them when I sit with the full timeline of the universe's death. The Stoic reminder that what matters is what we do with the time we have. The Epicurean reassurance that the end, when it comes, will not be experienced as loss. The Buddhist invitation to be fully present in this extraordinary, brief, and unrepeatable moment. And there's something else, something that comes not from philosophy, but from science itself. The fact that the universe is dying is, in a sense, the reason we exist. Stars die. When they die, they scatter the elements they have forged, carbon, oxygen, nitrogen, iron, into the interstellar medium. Those elements are incorporated into new stars and their planetary systems. They become the chemistry of life. They become us. Without stellar death, there is no carbon.
Without carbon, there is no chemistry complex enough for life.
Without the death of stars, the universe would be a place of pure hydrogen and helium, with no possibility of the molecular complexity that consciousness requires. We exist because stars have been dying for billions of years. We are made of stellar corpses, animated by the energy of a still living star on a planet that formed from the debris of stellar death. The death of the universe is not separate from our existence. It is continuous with it. We are part of the process by which the universe transforms itself from a simple state into a complex one, and then slowly, over vast timescales, back into something simple again. We are a brief, brilliant eddy in that flow, a place where the universe became complex enough to look at itself. And now we are looking. Now we are asking what it all means. Now we are calculating the timescales and reading the physics and trying to understand from the inside what the universe is doing. That, I think, is not a small thing. It is, perhaps, the most extraordinary thing the universe has ever done. It made something that could understand it. In 13.8 billion years, the universe went from a hot, dense plasma of elementary particles to a being that can calculate the timeline of the universe's own death. That arc, from the Big Bang to cosmologists mapping the heat death, is one of the most remarkable arcs in the history of anything. And we are at the end of that arc. Or rather, we are a point on it. The arc continues, presumably, for some time. Other minds may arise on other planets, in other star systems, during the remaining hundreds of trillions of years of the stelliferous era. Some of them may understand more than we do. Some of them may find ways to flourish in the degenerate era that we cannot currently conceive. The story of mind in the universe may be longer and richer than we know. But here, now, at this particular point on the arc, we have something remarkable. We have enough knowledge to see the shape of the whole story. Not every detail, far from it, but the broad shape. The beginning, 13.8 billion years ago, in fire and light. The middle, where we are now, in the warmth of living stars. The long end, in darkness and cold, as the stars go out one by one and the black holes evaporate, and the universe settles into its final, endless night. We can see that arc. We can hold it in our minds. We can talk about it. And that is a form of light, different from the light of stars, that might persist a little longer than the physical light. Not forever. Nothing persists forever. But for now, right now, the light of understanding is burning, here at Void Atlas, and wherever you are watching this. And that is worth something. That is worth everything. This is Void Atlas. I'm your host. The universe is already dying, and it is still the most extraordinary place in existence. Thank you for being here. Subscribe. Come back. We'll keep watching the stars as long as they're there.